happy to be here, and yeah, we'll see what comes next. The title of my work is The Sailing Efficiency and Course-Keeping Ability of Wind Assist, and that, I guess, if you were to look at it categorically, is the two main topics of my work. I've been working inside the Sail Assist group at the TU Delft, under the supervision of Lex Koning and also René Huismans. So to introduce, this is a wind assist ship propulsion. The basic idea is to replace main engine power with available wind assist power. And in this way you can reduce the fuel consumption. This is a key transition technology for the maritime sector. And it's there as a viable possibility for retrofit and also for a new build. So here in the pictures are a few examples of wind assist propulsion systems which are operating today. For example, the Flettner rotor in the image. This is, say, a modern version of a sail. It's quite efficient per surface area. So my own research was focused on the hydromechanics of wind assist. And there I could categorize it again according to the scientific methodology. That is, on the one hand, RAND CFD simulations, and on the other hand, towing tank experiments. So these are then collected in the book in chapter 3 and chapter 4. Finally, because my part was only, say, one detailed aspect of the work, and whereas the rest of the Sail Assist group was busy also with aerodynamics, that's my colleague Giovanni, and also marine engineering, that's Arthur Vrijdag, who's also here in the public today. Finally, the main deliverable for my work was to come up with a modeling which can be scaled up or scaled down, say, depending on the analysis context. In some cases, you will have quite a lot of information about the ship, and then you can come up with a sort of all singing and all dancing model. But in most cases, this is not the case. For example, in global shipping analysis using AIS data, you will have quite a limited number of data inputs. And you should also keep in mind that the analysis time, say, the computation time, will make it quite unfeasible to work it out in a high level of detail. So what happens when a large ship goes sailing? This is an example of one of the simulation results from the RAND CFD database that I've compiled as one of the main outputs of my research. First of all, along the bow of the ship, there is quite a distinct pressure peak. This is associated with a normal lifting profile. And then farther aft along the ship, there is an underpressure. That is from the monk moment. And this is a key design issue. This is a destabilizing effect and requires careful attention. Finally, these were more or less well known, but what is an interesting interaction is with a vessel heeling angle, that in fact the pressure field near the shoulders especially will experience an expansion or a contraction. So you can see a further interaction with the wave system of the ship. Good Christ. Excuse me. So that's, say, the first topic in my own research. That is the sailing efficiency of the ship, or any change in sailing resistance. Now, the first equation, which you see here, is the expression for the P-WASP, that is the available wind assist power. Some of you may recognize it from the EEDI formula. That is the current, say, energy efficiency metric which they have for large ships by the International Maritime Organization. However, in this expression there is no term representing any change in resistance for the having to do with the sailing condition. So that's the first topic in my own research. And this is because, as I was saying before, considering the modeling context, it would be unrealistic to introduce the, say, refinements in operating constraints, for example, and so on. This result is presented in the polar diagram on the side here. And you can see that, for reference, this is quite a small ship with a installed power of maybe 1.3 megawatts. So there are quite some areas where full sailing is possible. Now, the Delft Wind Assist series is following the research line from the towing tank, where systematic variations in hull form are tested or experimentally, or in my case it was done with a numerical simulation. And it's in this way you can generalize the modeling to accommodate a generic ship. So you can identify trends in vessel behavior based on hull form parameters. And we've composed a series of 3 parent hulls. That first of all, a general cargo ship, a deaderized series, which is approximately based on the old sailing ships from the last century. And then finally, a low CP series, which I think is really the low-hanging fruit at the moment. Because a key barrier for wind assist is that you have, in say, the supply chain and logistics arrangement in the present, say, global supply chain, not much transparency. If you find a product on your shelf, it's hard to say which kind of ship brought him there. And so with a ferry or a cruise ship, you're very close to your public. So now, especially in Europe, there's of course a broader consensus around climate change. And then the green image can be worth quite some money. So this is actually work continuing on with the simulation work that we try to train a neural network or an artificial intelligence model to replicate this response surface. Actually, it's work that's not in the present thesis. We finished it last week. And only to show here that it's apparently quite effective. You see in the black star is the results from the artificial intelligence model. And it's able to replicate the response surface at well, really a very small fraction of the computation time. So what this means is that it brings, say, more refined modeling into the reach of a modeling context where previously this would be inaccessible. Because, for example, a towing tank experiment or a RAN CFD run, that's a computationally intensive operation. The second topic, say categorically in my work, has to do with the course keeping, or if you're familiar from sailing, this is the helm balance of the ship. So here again is an image from the simulation where you have the wake field and then also the transverse force. And this distribution can be represented with a force acting at a distance, and this distance is in fact the center of lateral resistance. And you see that it's quite far ahead of the ship, which means that a corrective action is needed by the rudder. And this is due to this monk moment, which I talked about before. Crikey. Okay, so yeah, this is the monk moment. In principle, a linear destabilizing reaction. And then, just to note, in the aft here, there will be some separation behavior along the aft side body, which will dampen this effect somewhat. I show some results from the experimental work where you have this quantity, the center of lateral resistance, plotted with respect to the midship. So especially in this case, you have a very unforgiving ship, by the way, with a pram-shaped afterbody. So the balance of the ship is unforgiving, as I say. Now with the addition of a rudder, the center of lateral resistance comes aft somewhat, but still insufficient to sail a straight course. And then with the addition of these bilge keels along the aft body, in this case, and here, you can see quite a nice improvement for the balance of the ship. So, of course, it's possible to steer with the rudder, but should better maneuver with the rudder, and the ship ought to be able to sail itself in some sense. That's really the 5th time. Here are some final results for the bilge keels, and just to underscore that not only is the sailing efficiency improved, that's on the left-hand figure, but this yawing moment, as you see for a series of dead-rise specials, here essentially the after body in the pram is filled in with a skeg. And then you see, in fact, that there's a reduction in this linear effect for the yaw moment. So as you see, the red line in this figure is pretty well a straight line. which is as you expect from what is basically a linear effect. But then with the inclusion of these appendages, that this moment is reduced markedly. And this is again having to do with a lateral edge vortex separation, as you see also on the cover of my book. I've shown it here in the top as well. That's a very nice effect. Finally, to place my research in, say, the broader analysis context, the work that I've done at the university, also together with Arthur Vrijdag and my colleague Giovanni Bordonia, has been to do with a modeling for the vessel. Whereas to consider, say, the optimization of wind assist operation in, say, a real wind condition and over a proper route, then you have to talk to the climatologists, and we have some good colleagues at the Tyndall Center who have been helping us with this. And then finally, this information is passed on to somebody who has an understanding of economics and can make a proper assessment for the payback period. So in the meantime, we've done a number of case studies together with this consortium. I'll just run through some quick results here. A good way to look at the performance of a sailing ship is by considering the ratio of the sail area and displacement. And this is, since displacement is well correlated with the installed power, this gives you an idea of what kind of savings are possible. We did some very different types of ships. For example, a small coaster, which is what I showed you in the first slide, has an installed power of maybe 1 megawatt. And in contrast, this Panamax-sized ship is on the order of 10 megawatts. So it's really quite a big difference. And you can see correspondingly that this ratio also changes. One other point that I should say here is that, whereas the installed power, this large diesel engine, you have something on the order of 10 megawatts, so that the possibility to replace this engine power with wind assist power is limited. Yeah, I mean, you cannot put a very large sail on a ship without getting in trouble with bridges, for example. So I think I need to wrap it up here. To say a bit more about ongoing work, first of all, after the finish of my Ph.D., I joined with my colleague Giovanni, and we tried to move into the private sector and continue this work. I suggest that there should be further towing tank experiments to further validate the flow fields, especially in the context of this artificial intelligence modeling. There's quite some work remaining to be done in terms of propagation of errors. And then finally, also in the context of this artificial intelligence modeling, that we should have further holes in the series, further training data for the model. And then there's a possibility to extract much more information from the flow field. For example, the angle of attack at the appendages, the wake fraction for the propeller, and really much more. So with that, I close the presentation. Thank you very much.
van Nicolaas Johan van der Kolk, Master of Science in Marine Technology. I request the promovendus to take his position behind the lectern. Ladies and gentlemen, you may have already noticed that I switched to English after my first opening sentence into Dutch. The whole ceremony will be held in English. I will first welcome the committee members who are joining us online. And we can see them on the screen. And I will first introduce to you Dr. Viola. He is from Edinburgh University. And he's on the screen at the bottom left.
Ja. Oké, eindelijk. Via de telefoon dan maar.
Maybe I have a message for the members online. Please switch off your microphones so that we do not hear your conversation. Yeah? Thanks. Then we have the other opponent, Dr. Wakkers. He's from the École Centrale de Nantes. And he's on the very bottom left on the screen.
Still audible?
Yeah. Thanks.
Okay. Perfect.
Then we have Professor Van Rey. He's from the TU Delft, from the Faculty of Mechanical, Maritime and Materials Engineering.
You hear me
and he's replacing Dr. Wilson.
Is it clear or?
Perfect.
Yeah.
It's very clear.
Professor Hopman.
I don't know why, but now.
Professor Hopman. Can you be silent? Let me say it in that way. Because otherwise you're disturbing our conversation. Thanks. Well, the first is Professor Hopman, and he is on the screen at the bottom right, so welcome. He's from the Faculty of Mechanical, Maritime and Materials Engineering of the TU Delft. Then we have Dr. Koenig. He is in the middle, on the top of the screen. He's from the faculty, also of the Faculty of Mechanical, Maritime and Materials Engineering. And then we have the promoters. Right of me, the co-promoter, Dr. Akkerman, and left, Professor Huisman, and they are both from the TU Delft, from the Faculty of Mechanical, Maritime and Materials Engineering. I'm Professor Van Breugel. I'm from the Faculty of Civil Engineering and Geosciences, and it is my pleasure and honor to chair this session. I would now like to open the opposition, and for that I will give the floor to the first opponent, Dr. Viola. The floor is yours. Dr. Viola, the floor is yours. Can you hear us? Dr. Viola, can you hear us? He gives the impression that he does not hear us. Dr. Viola, can you hear us? This is the problem with a live broadcasting. Dr. Viola. I suggest that we ask for the technicians to see whether he can come in contact, and meanwhile I'll switch to Dr. Wakkers to start with the questions. Dr. Wakker, do you hear us? He also does not hear us. There is something wrong with the connections. I'm afraid that they do not hear us. Yes? Yeah. So there will be a technician who is looking after this problem, and most probably it will be solved in a short time. Our apologies for this one. This can happen. Well, this is an extra test for the candidate as well. So waiting for the questions he's... Yeah, you're running out of time, yeah. Well, you're buying time. You can also say it in that way, yes? And one of the online opponents, can one of you hear us? Or are you all disconnected? Yes, they are all disconnected. To fill up one minute is possible for me, but when it is longer, then it becomes, I do not know what I have to say anymore. Yes. Now, well, it is not so nice if we start with the promoters. If it would be an other independent member here, we could do it. Yes, but to start with the promoters is not so nice.
Can you hear us?
Yes.
And one of you, one of the online members, can you hear us?
Yeah.
Okay, okay. It seems that we are back again. Okay. There was an interruption of the connection, I think. Anyway, for those committee members who are online, I've introduced you all. Meanwhile, and I would like to invite the first opponent, Dr. Viola. Can you start your question, please?
Dear promovendus, I would like to congratulate for your thesis, which I found very interesting and extremely wide in the amount of science that has been explored, particularly from the hydrodynamics point of view. I found, however, that the aerodynamics was left a little bit behind, and I would like some clarification of how you have considered the thrust provided by the flattener rotors of this boat.
Hooggeleerde opponent, thank you very much for your question and for your time in reviewing the thesis. Indeed, the topic of aerodynamics falls outside of my own research scope. That is because another colleague within the Sail Assist group at TU Delft was busy with this as, say, for the entirety of his Ph.D. study. So we worked together on the integrated system model, but my own, say, scientific effort was focused truly below the surface.
Thank you, worthy promovendus. I understand the authors that is now being clarified. Let me then ask you a different question about the hydrodynamics then. I noticed that you have undertaken both simulations of the hull resistance at module scale and at full scale. Can you clarify what are being your considerations to scale the grid and the module more in general from module scale to full scale?
Hooggeleerde opponent, thank you for your question. Yes, that's correct. Following the normal towing tank scaling procedure would be an option. However, with the availability of, say, well-developed RANS packages, performing a full-scale simulation is within reach. And this is, in fact, the methodology which I adopted. Thereby, you resolve not only the Froude similarity, but you can also resolve any Reynolds scaling difficulties.
Well, you have done a very comprehensive study of the uncertainty for all of the experiments that have been undertaken. And for the simulations, I would expect the same. And therefore, there must be significant differences in the uncertainty between the model scale and the full scale, because the grid will be different and the Reynolds numbers will be very significantly different, and therefore the dimension of the grid will have a different impact between the two simulations. Would you like to comment on this?
You're absolutely correct. This is, I would say, a very tricky question. I should say, for example, pointing to the establishment of these friction lines at say, transition to fully developed turbulent flow, that in fact at the high Reynolds number, that, be careful what I say here, but I should expect that the model error should at least not be larger, since these models are often calibrated at, say, high Reynolds numbers. But the uncertainty quantification for the simulation was in fact done at model scale, and this was because of the formal validation procedure, where in fact we're comparing an experiment with a simulation one-to-one.
When you have undertaken the uncertainty analysis at model scale, you might have noticed that the grid resolution plays a major role in the uncertainty. Now, your grid resolution will be very different at full scale. Therefore, how would you expect to have a similar results in terms of uncertainty at model scale and full scale if you keep the same grid?
Well, I have to say that for the full-scale simulations that the grid was somewhat different, especially near to the wall, that there has to be a different treatment for the boundary layer, and that in fact the logarithmic law boundary layer, I think so long as the gradient at the wall is sufficiently resolved, that's the effective grid resolution. In fact, this is a problematic issue for most grid conversion studies, is these logarithmic boundary layers. Which is to say that so long as the empirical model, this log law approach, so long as the refinement is sufficient to capture the gradients for the shear stress, then I do not consider that this should be difficulty. In fact, if I to follow up that the convergence rate for these resistance calculations in terms of the observed order of convergence is in fact unusually high compared to what you would expect. And that has to do in fact with the modeling at the wall. Does that answer your question adequately?
I think that the reason of concern is that when we scale the results from model scale, and we use any ITTC procedures to do so, and then we compare with full-scale CFD, the assumptions in the thesis is that the full-scale CFD simulation would have been more reliable, and I have a profound doubt about it. I really question the fact that using runs to change of orders of magnitude the Reynolds number might actually lead to more accurate results than an ITTC or established formulations. And without having done any uncertainty analysis about this, it's very difficult to comment because we do not know which one is the uncertainty at scale. So when we compare two results, we don't have error bars to ensure that the error bars is small enough compared to the differences that we observe.
This is true. I have to say it would be possible to follow the ITTC scaling procedure, and in fact this was there under chapter 3 at the end, and quite a good match was found between model scale and full scale results. At least if you consider also the uncertainty and the form factor, then I think the match, it shouldn't be surprising in fact that the match is good, since these friction lines are sort of attuned, if you will, with full scale data. However, in the case of maneuvering forces, it's much less clear how to do the scaling. And in this sense, I would maintain that the full-scale simulation is, since it is possible, it is more appropriate, considering especially behavior of a ship in drift and the separation phenomena along the bilges of the ship, which are quite Reynolds dependent.
So to conclude, to your experience, what would be your take, which is your conclusions about the differences between undertaking model scale simulation and scaling the results rather than undertaking full scale simulations?
Again, because there exists some dubio, if you will, regarding the scaling procedure for maneuvering forces, I would prefer a full-scale simulation if it is possible. And that it sort of precludes, for example, a near-wall modeling, which is then, say, the price that you pay. Or it becomes much less realistic to do a near-wall modeling for the turbulence at the boundary layer in the case of a full-scale simulation.
Worthy promovendus, thank you very much. I'm satisfied with the answers. Mein Herr Director, I'll leave you to my other colleagues. Thank you.
Good. Thank you very much, Dr. Viola, for taking part in the opposition. And indeed, I would like to move on. I'm going to give the floor to Dr. Wakkers.
Thank you, meneer Director. Well, the promovendus, first of all, congratulations on performing such a multidisciplinary project in such a coherent manner. Because you treat many subjects, but at the end they all come together. And also, I quite admire the way in which you discussed uncertainty and in which you took into account uncertainties throughout the discussion, which is, I think, an example for us all. Concerning questions, I would like to start by coming back to the discussion about model scale and full scale. Now, specifically about appendage design. Because in chapter 4, you discuss appendage design based on model scale experiments, where I think your approach is to get rid of too much boundary layer influence, to have appendages that are way too big, that really stick out through the boundary layer. How could you use this kind of information to design full-scale appendages that have the correct Reynolds effect, especially bilge keels, which, as you indicate, are boundary layer influences? How would you design these in full scale?
Hooggeleerde opponent, thank you for your time and attention in reviewing my thesis and for an interesting question. Indeed, the working principle for a bilge keel is the promotion of flow separation at, say, an angle of a drift angle where otherwise it would not yet happen along the bilges, say the four-body side vortex. In fact, one of the key scaling issues in the experiment was to ensure that this separation effect was in fact happening. And for this reason, we tested a series of keels with increasing height. And in fact, quite a distinct change in behavior was observed around the region of the fully developed boundary layer. So that is to say, for the dimensioning of a scale in a full-scale, of a keel in a full-scale application, it would be essential to protrude through the boundary layer. But this would, of course, happen much sooner when you're looking at a full-scale appendage arrangement.
Okay, but I think that if your bilge keel size is of the order of the boundary layer, then it would still be very important to have the correct influence of the boundary layer on a specific part of the bilge keel. How can you be sure that you get the right effect?
I believe there is a lot of detailed simulation possible to identify indeed where are the limiting streamlines and how to arrange the fine positioning of the keel. In the case of the experimental work, the real goal was to ensure that the dimensioning is appropriate. That is to say, to ensure that the rather too thick model scale boundary layer doesn't simply wash over the keel without noticing, if you will. To make sure that really that this vortex sheet is caused to separate from the hull.
Okay, thanks for your answer. I would like to go to a completely different topic, which is the subject of validation. And there's this concept of validation at a certain validation level, which indicates that the difference between experiments and simulations is within a tolerance imposed by the numerical and experimental uncertainties. This has nothing to do with your work, but I've never been really satisfied in this concept. But because it basically means that if you have large enough numerical uncertainties, you can prove anything. So I would like to have your take on this, and also in the same time, rather than talking about validation at a certain level, can you motivate that your results are accurate enough to get to the conclusions you have?
Hooggeleerde opponent, thank you for your question. This is indeed a very interesting topic. What you say regarding the numerical uncertainty is true. However, I think it must be considered also against the available experimental precision, which is to say that it wouldn't make too much sense to have a very well-resolved or say high-resolution simulation effort with maybe sloppy validation data. So there must be somehow commensurate the two contributions to the validation level. That's the first thing I would say there. And then regarding the level of uncertainty in our own work, well, the first thing I would say is that since we've achieved parity, at least with the experimental facility that we have here at the towing tank, then I think that in some sense is satisfying, because in fact the validation level will depend on both of those contributions. And then regarding the actual effects that we hope to discern in, say, simulation of systematically varied hull forms, for example, or different operating conditions. Yeah, it's a very sobering thing to see, in fact, to look at an uncertainty bar and then try to identify a systematic trend. But I think as long as you keep track of your bookkeeping, it should be possible to identify real effects. That's sort of the utility of the uncertainty assessment, I suppose.
And so are your simulations actually accurate enough for what you want to use them for?
Well, unequivocally, yes. We have, for example, in the last piece of work, we have managed to replicate this response surface with a neural network model. And there, the uncertainties that come out are of the same order as the comparison errors. And, well, you should of course be careful what you say here, but compared, for example, with a standard maneuvering model, where based on a normal drift sweep with a quite limited number of data sets, then the uncertainty in a maneuvering coefficient is also quite inhibitive if you look at it carefully. Does that answer your question?
Yep. Yeah. Thank you very much. I would like to conclude with a question directly on CFD, because of course I saw with great interest the choices you made for the different modeling aspects, the mesh, the turbulence model, etc. I wondered if you had a bit more CPU. So say you could have doubled, tripled your computation budget. Mm-hmm. What would you have changed in your simulation? What would be the most cost-effective improvement in your simulations?
I believe in this respect, I would first extend the drift and heel sweep to include more angles. This I've noticed, especially for any quadratic or third-order term, that it's impossible. Of course, if you have 6 points and you fit a third-order model, then you have, it's very problematic. Let's say it this way. Yeah.
And regarding a single computation, if you had to make a single simulation better?
Yeah, in this case, I think a near-wall model is the logical next step. and this at full scale becomes quite challenging, especially in the mesh generation. However, since a fair portion of the separation behavior, which is relevant, has to do with bare hull, say, curved surface, adverse pressure gradient type separation, that this is something which you ought to properly resolve the boundary layer for.
Okay, that perfectly answers my questions.
Okay, thank you very much, Dr. Wakkers, for contributing to the defense ceremony and being an opponent in this committee. And I would like to move on and give the floor to Professor Van der Rey.
Ja, dank u wel, meneer de rector. Waarde promovendus, thank you for your thesis, which I read with a lot of interest. I have some questions on chapter 5, where you integrate everything and also look at the economics of the system. First small question, that's on page 135, where you write down when the ship sails into the wind, then the fuel savings will be 0. But isn't it so that if you are sailing in the wind and you have this added resistance of this rotor, so then your fuel savings should be negative?
Hooggeleerde opponent, thank you for the question. You are right that there is a, this actually has to do with I would say a shortcoming in our modeling, that is that the propulsive requirements, especially sailing upwind, will be in excess of the engine operating envelope. If you see on the page there, I think it's figure 5.9 in my document, that some of these conditions when sailing upwind would be, in fact, impossible conditions for the ship. Ordinarily...
You mean sailing at the speed that you want to achieve?
That's correct. Ordinarily, for added resistance in waves, you would introduce, say, a speed reduction polar. But at this stage in the modeling, we don't have anything along those lines. And the point that I wanted to underscore in the text, which was, I think you're right that there's a mistake there, that in fact when you're sailing upwind and you compare with the reference case, which would be identical ship with no rotor, that a ship with a rotor should have a higher windage, indeed.
Yeah.
But neither of these ships would hold this speed. That's the point, yeah.
Yeah, that's correct. Okay, then I move over to your economical analysis, where you calculate the payback period. That's figure 5.15. Of course, at the moment, I looked up the bunker prices yesterday. It was around $320 per ton, so that's really not quite dramatic for the payback period, but let's hope that will be not a permanent situation for the offshore. But in the economical analysis, you take into account the fuel savings, but there are also, I think, other economical effects. For instance, how did you include the added weight of these rotors, because these are quite heavy. The forces acting on them are of the same order of magnitude as the propulsion forces. There's a lot of dynamics involved. So that means you add a lot of weight to the vessel, which is reducing its cargo. So how large is this effect in the economical analysis?
That is correct, what you say. Thank you for the question. In fact, we made a simplification for this case. It could be that you could reduce the, say, deadweight capacity of the ship. However, we also consider that, in principle, it would be possible to carry less fuel, which could perhaps offset some of this weight loss. And, well, next to that, compared with the, say, tonnage of the ship, the weight of the installation, and of course, it could be that there is some structural steel necessary as well. But it was not a significant part. If I had to think from the top of my head, it's maybe 5%, or less than 5%.
That's only for the drive system and the rotors then, not for the structural improvements, I guess.
That's possible, yeah.
Okay, but it's not, in fact, it's not really included at the moment.
No, that's correct.
And if you would look at, for instance, in figure 5.12, there you compare two situations where you have a shortest route condition and a optimum or optimum fuel safe condition, where the green line. If you would optimize for economical benefit, where do you expect? Is it then, would the result be close to the shortest route or the other condition?
I think this has a lot to do with conditions in, or the availability of ships in the maritime fleet. If there's an oversupply of ships, then it can be that a vessel can spend an extra day or 4 at sea without any penalty. On the other hand, if ships are in high demand, this will not be feasible.
Mm-hmm. Yeah.
So I think it depends really on say, logistics at that point. And that, I suppose, falls outside of the scope of our study.
Yeah. Okay, that's clear. You focused on these rotors for the wind propulsion. Is this the most? Is this the best system for these?
No. No, certainly not. There's many systems available now based on various physical phenomena. Rotors happens to be the topic of my colleague Giovanni, who has defended his aerodynamics, his thesis focused on the aerodynamics. And because we work in the same group, for this reason, the case study involved a ship with flattener rotors.
Okay. So it's just a decision. Then, when we move over to figure 5.9, where you have the power grid of the vessel, where it was decided to have separate diesels for the rotors and a main diesel for the propulsion. And that has, I think, as a side effect that this main diesel engine will often run not full power, but maybe only half power or maybe 20% idle almost. That means that the costs for maintenance of these combustion engines will increase, I guess. But that's what's your opinion on that?
My opinion is that there's quite a lot of space available still to optimize the main propulsion of these vessels. The case of this retrofit, which was using an existing arrangement for marine engineering. Indeed, for the sake of simplicity, we take, for example, a fixed pitch propeller, and then as you see here on the figure, including the engine speed and brake power and the envelope for the engine, that in fact, for example, besides the maintenance cost, also the specific fuel consumption is impacted. Mm-hmm. So it's an off-design condition, and in fact, a lot of the normal design approaches for these engines are not von pas anymore.
Yeah. Okay, so that's also leaves some room for improvement. Okay, well, Waarde promovendus, that concludes my questions. Thank you.
Thank you very much.
Okay, thank you very much, Professor Van Rey, for your contribution. I would like to proceed to give the floor to Professor Hopman.
Dank u, meneer de rector. Waarde promovendus, to start with one of your propositions, I would like to discuss proposition number 5.
Waarde promovendus, may I invite you to read out proposition number 5?
widespread adoption of wind assist is necessary to offset the CO2 emissions associated with this research.
Yes, also knowing that you would like to start a business selling these systems or assist ship designers to do so, but to my opinion, this is not a very positive message, because this could mean that the advantages of using wind assist are very limited, or from a CO2 point of view, it would have been better if you would have done research on another topic with more impact on CO2 reduction.
Zeer geleerde opponent. Indeed, it perhaps is a bit tongue-in-cheek, and maybe, but in any case, what I should say, as we see now today with the coronavirus, a lot of the travel obligations of academics has been severely curtailed, and I think this should be a positive thing. Yeah, and then next to that, there's also the point of the HPC computing time, which has also been demonstrated to have quite some climate impact.
Yeah. Do you still think that...
Yes. To answer your question, I maintain that the wind assist remains a key transition technology for the maritime sector, for the technology readiness, and for the sake that retrofits are well possible. It's been demonstrated in the meantime that the embedded carbon in the presently existing fleet already puts us beyond the, say, planetary boundary, which is to say that retrofits is really the order of the day. And wind assist, yeah, sorry?
I understand the underlying message, but I'm wondering if this, to use this as a message to your possible clients or something like that, I'm not sure if it actually works, but okay. Can I ask another question? As a ship designer, also referring to page 12, which shows a 3D plot of a ship whereby some ratios have been varied, the CM value and the CP. Yourself, you have paid specific attention to bilge keels, positioning, etc. But now, as a more generic advice to ship designers, if I compare an ordinary ship without wind assist, I integrate a wind assist system from the beginning onwards, could you give me some advice? What will change to the ship with respect to dimensions, ratios, coefficients, appendages?
Yeah. Thank you for your question. That's a very interesting point to elaborate on. I think, first of all, it would be quite clear to prioritize the draft over the beam. I think this would be a place to start. A very fine entry might be helpful. I think a dead rise 4, as we see now from a recent ship from Denmark. It's a very nice ship that's come out from SSPA. Yeah, it will be necessary to provide larger rudders, I believe. I think one of the most interesting interaction effects which I've observed is between the main propulsor and the wash over the propeller, that the conventional rudder for a ship is rather underdimensioned, and that in the absence of main propeller thrust, that this rudder becomes quite ineffective, absent a wash, if you will. So yeah, there can be some improvement for the perhaps 2 rudders, maybe an appropriate thing to do.
Okay.
Something along these.
Referring to the first option you explained, if you increase the draft, it probably will have effect on other dimensions or coefficients, because I don't think you would increase draft by just adding weight. So what would be the other effects?
Well, I think reducing the CP4 is a sensible choice. That way you could take care of some of the volume. I think it would be sensible to maintain a rather hard bilge. This is related to the sailing efficiency. It may be wise to take care of the wash going into the propeller and rudder, since as a hybrid ship, it's important that the propeller experiences a clean, say, wake fraction. And especially when operating with a drift angle, there can be, as some work from Marin recently, that there is a vortex which comes, say, from the bow or near the bow of the ship, which finds its way to the propeller disc, which is not ideal.
Okay, that makes it clear to me. Thank you. I had another question, also related to your ideas about starting a business. Referring to the IMO ambition, also mentioned in your thesis, to achieve also the EU has similar ambition, but would like a zero emission solution. The technology would be available to at least apply zero emission solutions for ships, seagoing vessels. It will be used more often by 2050. Keeping that in mind, would that mean that the wind assist is more a temporary solution during transition towards zero emission? What is your view on that? Because could it help in combination with other zero emission propulsion systems?
Thank you for the question. I believe I understand the gist of it. I think it would be important to think about wind assist as part of a package of solutions, say. For example, you can think of hydrogen next to it. But if you are able to absorb some portion of the propulsive requirements with wind assist, then the remaining propulsion systems can be of a smaller dimension, which is quite a help. And then finally, to your other point regarding, say, the temporary nature of wind assist uptake, I believe that was the idea. I would say that following also on the point from before, that the research showing that embedded carbon in the present day fleet is already in excess of, say, the planetary boundary, and that operation and so simply waiting for service life to end and coming up with a new fleet with indeed zero emissions, alternative fuels, that this solution, well, it will take too long simply, and it will be too late, at least according to the research that I've seen.
Okay, but again, I mean, you're referring to it might reduce the installed power, but from your calculations at the end, the main advantage, I think, comes from the reduced fuel costs over 8 to 9 years, the payback period, and not the smaller effect on the smaller installed power.
You are correct. In this case, it's a retrofit case. So we don't change anything for the normal propulsion system. But if you were to begin from a new build stage, or perhaps repower the ship, then there can be, it would be possible to install a smaller engine, also in line with the new slow steaming rules.
But could it be, because at the end, up to now we use the EEDI, it could mean if the CO2 emissions are zero, we can, in theory, increase our speed again. So there is no need for power reduction. So I'm not so sure if the actual effect, taken into account zero emission solutions, integrated with sail assist, if that would be the choice.
It would surely be a more complex vessel, but the fact remains that there is an available wind assist power as long as the wind is blowing, and it seems a pity not to go sailing.
Professor Hopman, are you satisfied with the answer so far?
Thank you.
Good. Thanks a lot for taking part in the opposition. I would like to proceed to give the floor to Dr. Koenig.
Thank you, Mr. Chairman, meneer de rector. Waarde promovendus, als eerst wil ik toch even noemen dat ik het een interessant onderwerp en een interessante studie vind. Oh, sorry, in English, neem ik maar. Dat is an interesting research, and I read the work with great interest. So thank you for that. And I would like to ask a few questions regarding the yaw moment, the Munk moment, or however you call it. We know from big sailing ships, clippers, etc., that this yaw moment, Munk moment, has a great effect on the balance, the yaw balance of the ship. And in normal life with those ships, it means that they have to reduce sail just in order to keep control over the directional stability of the craft. Which means that there is an interaction between the behavior and your power that you can deliver for propelling the ship. My first question on this issue would, can you give me any idea for the ships that you have investigated, how much power loss there is due to this imbalance?
Hooggeleerde opponent, thank you for your question, and thank you for your time in reviewing my work and for your supervision in the last years. Well, in the case of the small coaster, that's the case for the Baltic Sea. This was the, say, a 5,000 deadweight ton ship. There, for any appreciable thrust benefit, or say wind assist, where the sails are really operating at a high level, then the rudder angle was up against the limits of 10 degrees, which we set. So that is to say that there would be an additional resistance from the rudder besides the normal, say, induced resistance of the hull itself. Sometimes for a racing yacht, it can be handy to operate with a small rudder angle. But I think in general, this is not preferred for the case of a wind assist ship.
No, but what I mean that this usually leads to the fact that you have to change your sail plan by taking away the aft sails or the mizzen or whatever, just in order to keep the boat in course able conditions. So you lose power. Have you any idea how much this is?
Yes, I think one way to look at this in a nice way would be to compare polar diagrams for wind assist devices where these operating constraints are considered. So for example, a maximum rudder angle against what is often shown as sort of a butterfly diagram with two nice lobes with no evidence of depowering at high wind speed. In fact, when you have something like 30 knots of wind, you should expect to be depowering at that stage. It would be quite illogical not to. And in fact, for the case in the final chapter in the Ph.D. work, this is with a 3-rotor arranged along the line of the deck. There, the aftmost rotor is depowering for situations when in fact the stability of the ship is compromised.
Yeah, but normally, as far as you understand it, this would mean that you have to sail or use the sails with a very forward position of the center of effort of the sails, which means even for rotors that you have to place the rotors in close proximity to each other instead of spreading them over the entire length of the ship, which means that you have interaction effects which doubtlessly negatively influence the efficiency.
Yeah, I follow your question now. Indeed, if it were possible to array, say, wind assist devices along the whole length of the deck, the length and breadth of the deck, this would be preferred. This speaks to, in fact, the second topic in my research, this core stability of the ships. It would be a key design issue, and especially for full realization of the potential of wind assist.
Yeah, I agree with that. And then let's say my final question for the time. If you have complete liberty to design a ship to have as minimal negative effect of this yaw imbalance, how would it look from a hydrodynamic point? What would the hull look like? Because now most hulls, and also your family of hulls, are actually designed along the lines of minimizing residuary resistance and frictional resistance, and maybe add an appendage to increase the position of move the position of the center of effort aft. But if you are free to do what you would like to do, which options would you consider?
Thank you for the question. This is a nice exercise. I would say that the dead rise angle can be attractive for mitigating this yawing moment. Indeed, as you say, the family of hulls which I have studied has this pram-shaped after body, which makes it rather unforgiving in terms of core stability. So with the inclusion of, say, a skeg aft, this already improves the picture considerably. As a general statement, I would say that we would rather not be controlling the ship with the rudder, that there should be a good balance in the ship fore and aft in terms of the hydrodynamics and the aerodynamics. And yeah, the rudder is there, of course, to maneuver, but there is also a possibility to include active, say, skegs or some foils arranged even forward along the ship. I think I mentioned before the ship from SSPA. This has in fact some quite nice appendages forward along the ship, really dedicated lifting appendages. I think that's a possibility, although I should say that's rather complex. I think such a system may rival the cost of a Flettner rotor eventually. So this is maybe not so attractive from an economic perspective.
No, but a final word, a cheap solution maybe could be to destroy the Munk moment.
Destroy it?
No, reduce it as much as possible.
Uh-huh.
And there are maybe ways of doing it?
Yeah, I believe with the inclusion of bilge keels along the aft side, you can promote this separation phenomena that is observed, I believe, in your own paper, that there can be a release, say, of the underpressure in the aft body of the ship. You can promote this effect with placement of bilge keels.
Okay. And that was all. Thank you.
Thank you very much, Dr. Koenig, for your contribution, and I would like to proceed to the committee members here present in the room, and then I would like to give the floor to the co-promoter, Dr. Akkerman.
Dank u wel, meneer de rector. Waarde promovendus, I have a question regarding proposition number 10.
Waarde promovendus, may I invite you to read out proposition number 10.
Market drivers are not adequate to promote the necessary technology transformation.
Yeah, so regarding that statement on page 153, I think it is, regarding chapter 5, you do conclude that there is a business case for wind assist. So how do you rhyme these two statements?
Zeer geleerde promotor, thank you very much for this question. You are right that they appear to be incongruous. However, a large part of the work in Chapter 5 was to consider wind assist operation inside of present-day market conditions, but also considering the possibility for the introduction of, for example, a carbon price, which is much talked about now, but of course doesn't exist yet. And next to that also the possibility for reducing your port fees. For example, if your ship has a certain EEDI measure, then it can also apply for a certificate as a green ship. And then you have a reduction in Rotterdam and also in many other harbors in Europe. However, as is also outlined at the back of the paper, Chapter 5, is that one of the key barriers for wind assist is this conundrum where if the owner is the operator, then he can benefit from the investment. But however, many ships are operated in several layers, that there is, say, an agent which looks for cargo, and it could be a time charter, or this really outside of my field, if I'm to be honest. But in that case, the person who makes the investment eventually cannot benefit. He has to increase the price for his ship on a time rate, if you will. And in that case, he doesn't become competitive any longer. This is called the market for lemons in economics.
So is it fair to conclude that at this stage the regulations are essential to make it?
Oh, absolutely. I would say that this is something which has to come from the government. I don't think this impetus will come from the market.
You think current expected rules in the future will then, in a sense, automatically favor sail assist, or do you think certain rules should be strengthened or formulated differently, or how would you envision that?
The way sail assist is written into the rule now is actually quite favorable for sail assist. Maybe not so physical, but quite favorable. So this, I would say, can stay as it is. European legislation is, in fact, I think now ongoing to take up the MEPC document. And as I understand, they're sort of leapfrogging each other. The IMO is trying to keep up with the EU because generally the sentiment in Europe is most advanced on this topic.
Satisfied with that?
Okay, thank you very much. I'd like to proceed to give the floor to the promoter, Professor Huismans.
Oh, excuse. A lot of questions are still on the table. I want to take you back some 5-6 years, where we started this study with some sort of general outlook of sail assist, how it will influence. Having gone through the whole route now, in retrospect, what do you think should have been on the table from day one more with the knowledge that you have now, and that we may proceed for maybe another candidate to go forward?
Hooggeachte promotor, thank you for your question. I would point to the vessel model, to this integrated modeling environment, where I had the possibility to, say, propose different modules for the hydromechanics, and then we could observe how this interacted also with the effects that Giovanni was able to elucidate, and also Arthur Vrijdag for marine engineering, and besides which, of course, the routing and the economics. I think this last piece of work, which is there in Chapter 5, has been in some way the most interesting.
Yeah, but that brings me to your proposition number 4. Maybe you can read that out.
Yeah.
By the promovendus, proposition number 4.
Characterizing vessel behavior using terms in regression polynomials is problematic.
Can you elucidate a little bit on the problematic? Because, as you say, if we know on beforehand, if we know more about the physics, just to do the fitting with the correct physics.
Yes.
Why is that problematic?
Well, it can be quite difficult to bring a meaning into a regression formula which has several layers. For example, in this latest neural network implementation, then it's quite a challenge to understand or to define, say, a meaning.
Thank you, Madam Beadle. May I request the candidate to go back to his seat in the room? Ladies and gentlemen, the committee will withdraw for further deliberation in the committee room. The session is adjourned.
Lopen.